How do you make the screen get bigger? You know what the keys are? So is it control plus sign? And function. It does that, but it doesn't move it any. Oh, well. Okay, there's Lewis. Yeah. I like having it up there because then I got the speaker through the projector. I'll run over and take roll real quick. Yeah, sounds like her. There she is, okay. Okay. Let's see. Okay, there we go. Okay, so on the announcements, the main thing I wanted to mention was the shoe thing here. Clarification on shoes, the updated dress code allows for athletic shoes only if they're completely black, no white or other colors, and that includes the logo. I don't know if that had been explained to you all or not. And then don't forget your diapers. I think Friday's the last day for that. There was something else. Oh, okay. So next week is when we have the all school Christmas chapel on Wednesday. So on Monday, there's no solar chapel, so don't wear chapel on Monday. But you will wear chapel on Wednesday. And then I guess some of y'all are doing speaking parts, I understand. Did y'all know that? We'll be letting you know. You remember what the solar or the Christmas chapel is? They sing a song and then we read scripture and then we sing a song and read scripture. And so they'll probably be having some of the sixth graders read, some of you guys read. Yeah, I think they do that every time. So yeah, you're on the list. They just haven't got to you yet. Any questions on announcements? All righty. Then we'll have prayer. Then we'll talk about the prayer requests. Yeah.
My grandpa, he had a mini stroke yesterday, so we had to stay overnight in the hospital last night. So hopefully he's good.
TIA, something like that. TAI.
Yes, I think something like that.
Ischemic.
It wasn't a full stroke.
Yeah.
It was just like his speech was off, and
My mom had one of those, yeah. But she hadn't had another one. They have good medicine for it.
yeah, he's taking. I think they're gonna give him probably something stronger because this is like his second one or something.
Probably. Yeah. Okay. And anything else? They're hoping to get those windows in, like you think about that. So because we can't get a occupancy permit until they finish those curved windows, and that's been a problem on the building. Okay, we'll pray. Lord, I thank you for today, and I thank you for the blessings you give us. Pray that you'll just forgive us as a school, as the body of Christ, as individuals, Lord. I pray that we can just do your will. And I pray that you'll bless Tyler's grandfather and help him to recover quickly and not have any more problems with that. That you'll just bless the students as they go through their day to day. And that you'll help us with the calculus as well. In Jesus' name, amen. My phone thought I was trying to tell it something. That's weird. So, recording me. Okay, so we're working on, you go to stop screen sharing. There we go. Now we can see the guys. We can hear them if we want, and they can see you. So we're still working on the handout, and I can answer questions on that. If you do finish, for some of you, I think Maddie, you're finished, right? Okay. Then we will be working on 4-6 tomorrow, and if you wanted to run it, go ahead. You could maybe do the cues or something. And so I wrote the assignment up there. It's also on Google Classroom, the assignment for tomorrow. And the next section, 4-6, we'll be doing that Thursday and Friday. Unless I'll just zip right through and I have to come up with more. Okay, so who has questions?
It says take a sign of this size, it's just me.
Yes. Same process. Do the base steps.
Mrs. Belcher,
Yes.
I have a question.
Let me turn your volume down. Hang on. Okay, what's that? Which one?
For number 17, what does it mean when it says use the properties from trigonometry along with the quotient rule to show how to derive the formula?
Okay, so they want you to find the derivative of tangent and show that the derivative of tangent is secant squared. And
Mhm.
so the way you do the properties from trigonometry is that you know that tangent is equal to sine over cosine. Okay, and then you use the quotient rule to take the derivative of sine x over cosine x.
Oh, okay.
And then you simplify it, and it should simplify to secant squared x.
Okay. Thank you.
What happened to Brian? Flip it out there. You didn't get anything else, did you?
You only have to get it 15 minutes later.
Right. I just didn't know if you would. Because that way they would have already changed it, so I'm gonna go change it. Yeah. Yeah. Right. Yeah, and by doing that, you're kind of proving, I mean, this isn't exactly a true proof because you're doing it for specific equation, not for any equation, but it will at least prove it's true for that one. But the X is there in there. You can say that. Okay, so now you can use the quotient rule, which was yeah, you didn't write it the UV way.
Oh,
Yeah, you can use that for sine is U, cosine is V.
and you take the one.
Yeah, and you derivative, and then you simplify it to secant squared. If you have trouble with that, let me know. Anybody be interested in a coupon for a free Whataburger Junior? We don't even have to buy anything else. And you get awards, you can fill it in yourself what you want to be awarded for. You don't have to do that. You can show it to your mom. She can do one time. Anybody else? Whataburger Junior? Got a lot of them. It expires on the 24th, so I think, better give them. Your question,
Yes.
yeah. Yeah, so you just need to put one X on the top, right?
Wait.
Right, okay, but you can have that tomato one on top too. Well, I was just thinking you could have it, that's just regular X on top, but either way. The 3 stays on top no matter what. You have 3 over and then X. Right. Yeah. And I don't think you can simplify that, even though the difference is squares, it wouldn't be. Yeah, I was thinking that people were getting all finished and everybody might finish before the end of the period today, but it's not. We'll just wait.
We have to learn.
No, I'm just saying.
Is
we're
that
gonna-
stuff we already know though, or is that something that we have to talk
We
about?
do not know that yet, but if you got done and you were bored and you wanted to do the cues or try it with the others, you could. You know, just didn't want to have you bored. Just- Okay, so you know the formula, you had a minus here? Okay,
And then
and then
negative.
so it makes it plus, right?
Yes.
Even plus, okay. And so you can combine that as the one, you split it up.
I think that's really like,
Because that would be one and that would be,
yeah.
yeah, and that would also actually work, but, the thing that you're gonna notice though, probably, is this thing right here, just to stand out from pre-cal. That if you just have that up here, like you would, you'd have cosine squared plus sine squared, it's equal to one, and you can fix on one.
Oh, I see.
And then you'll have cosine squared on the bottom. And then what's the reciprocal of cosine?
Okay, and then it needs to be this.
Yeah, so one over cosine squared is the same thing.
Wait, and then
And then- Okay, so you basically, doing this, right, taking the derivative of inverse secant of x cubed. So you're gonna use that formula, but instead of wherever there's an x, you're gonna put an x cubed, and then you'll also multiply it by the derivative of x cubed, because of the chain rule. So,
Oh,
Right.
okay, that's why it's doing that, because I just added.
right, and then, oh, but no, on this, you multiply this to power with power, you multiply,
Oh, okay.
it's like x cubed times x cubed.
Oh,
Okay, and then this, x right here will cancel through the x down here.
so then you're just.
Wait a minute, okay, this is going bad. Okay, so you had x cubed squared, so it's 3 times 2.
Oh.
Okay, that's right, okay. And then, no, because so these x's here can cancel here, but you're not taking anything out of the radical. Okay. Radical stays the same.
So you.
And then what happens?
Well, this is
Oh,
like an
okay.
X. So this would be like.
And then the square x squared, but it canceled with 2 of those, so it's no longer there.
So you don't really.
Oh, we
because
keep
it's
the 30.
Oh. Yeah, so then you
Yeah.
know that we're taking.
It's like you have 3x squared over x cubed. And so those two x's cancel 2 of these, so you just have a 1. So you have 3 in the x like that.
Oh, in the front.
Yeah, because you can have it all in one thing.
Oh.
Yeah, so all you have on top is the 3, and then and underneath you have the x, and then you have x to the
Oh,
6 minus 1.
and is that it?
I believe so.
Okay.
Okay, did you still have a question? What more did you have to do to this one? Is that the thing I think we were talking about? Yeah, and so since you're putting x cubed in, that's like the inside function. And so you take the derivative of the time secant, which you did, but then times the derivative of x cubed. Okay, so you didn't finish your chain rule here.
Do you not do the derivative of this one?
No, because you started out with inverse secant of x cubed. So the derivative is all of this with x cubed in there, and then times the derivative of x cubed. So like up here, you should put 3x squared. So this is where you went in, just plug them in, right?
Yes.
Yeah, so put
And then-
3x squared up here, and then you can simplify.
And then also is this the answer to like
It's way too simple.
what?
So I'm not, okay, so you have 1 over x cubed. That's what this means. Is the negative on here.
Oh, okay.
Yeah, on here they have the things about the negatives here, right here. X to the negative n equals 1 over x to the n. Okay, and then pretend like that's b, and that's that's u, and that's v, and use the quotient rule. Okay, then you should end up with the same thing that you have on this one.
Okay.
Because you have to put in two.
Okay, yeah, and at what point two, okay, and if you were to do a tangent line there, it would look like a little.
Oh, I thought it said you could stick.
After you find that.
Oh, is that where you have to do the variables?
Oh, yeah, they want you to, yeah, plot a line, so you gotta figure out the equation of the line.
Mrs. Belcher.
Yes, I'll be right there. Hang on a
Okay.
second. So that's what you change this to that,
Okay.
and then for that U and that V, use the quotient. Yes, how can I help you? I left my page somewhere. Hang on.
The quotient of 1 is just 1.
The derivative of 1 is 0.
Yeah, that's fine. It's 0.
Yeah, 0. Yes, who said that with that?
I
Lewis?
did. Yeah.
Okay, good to go.
I'm confused on what it's asking on number 19. Like,
Yeah, so they're talking about how we always use the power rule. We use the power rule for any power, whether it's a fraction or a decimal or a negative number. But we never did prove that it was true except for whole numbers. And so here they want you to show that it does work by taking the derivative. Like normally when you take the derivative of y equals x to the negative 3, you just use the power rule. But they want you to use the quotient rule. So you would first write it as 1 over x cubed, and then use the quotient rule.
oh, okay.
And then you should still get the same answer.
That just sounds like a lot more work than necessary.
Right, it does. So it's easier to use the product rule, but
Yeah.
they just, since we never did prove it for negative exponents, this is a good way to show it's true, at least for this particular one.
Oh, okay.
Yeah. No. Right. Oh, they have them over here. Right here, when you are multiplying, you add
Oh,
it there.
okay.
And then here, when you have power to power, you multiply. I'm on machine. Yeah, and so like 20. So that's that. So did you find out what this side was? Looks like, I mean, it is. This is what I have. Right, okay. So that's how you get this, that 1 minus x squared is that, it's square root of 1 minus a equals the square root of 1 squared minus x squared. Right. Yeah, the only problem is that when you took the derivative to get this part, you need to leave the inside function the same, like here you have x cubed and here you have x cubed squared. And so when you have that x cubed here, then the x cubed and the x squared can simplify. So you'll still have x cubed squared or x to the 6 here. So you did it at 2, right? And so if you put 2 into the original function, you can find out what the y value is. And use that formula. Now that's the derivative, that's not the actual function. You need to plug 2 into the actual function. And that would be the y value. Oh, yeah, you can just be irrational.
Okay. Is that thing?
Yes, because you could rewrite that as -3 and then put x up here, right, which is what you would get if you use the power rule.
Oh.
They're telling you can do it both ways. And it's much easier to use the power rule. But this way it proves that it still works and that the power rule works for negative numbers.
Okay. That makes sense. Okay, thank you.
Right, okay, this is similar to your book. Okay, it's gonna be the same process we're doing. Okay, so first you write down this y equals inverse sine of x, and then by taking the sign of both sides, you get sine of y equals just x, because the sine and inverse sine cancel each other.
Can I see how that would look, just so I can put it away in there?
Yeah, and in this case, we're using tangent, we just do it like that. And down here, they have secant, so they just secant in front of y. And then
How would they cancel out? This.
oh, let me show you. Like if you put that in your calculator with some number here, it would just end up giving you the number, whatever the number is, because if you take the inverse sine and you take the sine of the inverse sine, you're just going to be back to that because they undo each other. And so you just end up with that. So if you just had gone to this into the regular product problem, you would have gotten that.
So that's all the pages.
They're just saying that, we use the product with integral, power rule all the time.
Thank you.
But we never really proved that it works for negative exponential. Now this, using the quotient rule proves that it does work, at least for this one.
Mrs. Belcher, I have a question.
Yes. What you got?
For number 20, when it says take the sine of both sides, what would that look like?
So open your book to page
150.
150.
You say 150?
Yeah, 150. And so on 149, they asked the question about differentiate y equals the inverse tangent of x. And so on the top of page 150, they took the tangent of both sides. Okay, so let me do a share the screen thing, and so you can see what it looks like. There we go.
Differentiate implicitly.
Hmm?
Differentiate implicitly.
That's when you do the y prime thing. I can take the derivative of sine of y would be cosine of y times y prime. That's what they mean by See, and we haven't been taught the implicit yet, but they're just wanting you to use it anyway. Yeah, but it's a really, it's like a chain rule. So the derivative of the sine of something is the cosine of something times the derivative of something.
Can I see that after you? Because it's the next step in that problem.
Okay, then I'll just put it all up here. Okay, so going back to, this is number 20. Okay. Yeah. So if you do sine of y and then sine of inverse sine, see how I took the sine of both sides?
Mhm.
And so here that just stays sine of y. And over here that cancels that because they're inverse processes. If you took the inverse sine of x and then took the sine of the answer, you'd be back to x again, right?
Mhm.
Okay, and then the next step they say that then differentiate implicitly. Okay, so what means that we're going to take the derivative of both sides, and like the derivative of x with respect to x is just 1. But the derivative of sine of y with respect to x is the cosine of y times the derivative of y, which is y prime. That's called implicit derivation.
Mhm.
That's what they mean there. Differentiate implicitly. Okay, and then you're trying to find, since you could know what y is, you're trying to find y prime. Well, you have a y prime right here, so let's get it by itself. And so we're going to divide both sides by cosine y. And then it says, show how the formula can be written as an algebraic function of x. So here I have the derivative of y in terms of y, but I want the derivative of y in terms of x. So what I'm going to do is going back to this equation, and I'm going to put a triangle over here and call this angle y. Because I could rewrite x as x over 1. And I know that sine is opposite over hypotenuse. And so my opposite over here is going to equal x. And my hypotenuse here is going to equal 1. That makes sense?
Mhm.
And then the other side down here, we just call it the adjacent maybe, is going to be the square root of the hypotenuse squared, which is 1 squared, which is just 1, minus the opposite squared. That's just using Pythagorean theorem. Does that make sense?
Yes.
Okay, and so then we go back to here and we say, well, y prime is the cosine of y, but what if this is y, the cosine is the adjacent over the hypotenuse. So the adjacent is what you found there, 1 minus square root of x. I mean, 1 minus x squared. That's the adjacent over the hypotenuse. So we put a 1 here, right?
Mhm.
So that right there is the cosine of y. But you don't really need to write that 1 there. That doesn't do anything. You could just simplify it by just leaving it like that,
Okay.
which should be what you have on the formula sheet. We were doing this for a couple days before we went to Camp Eagle.
Oh,
So
okay.
it hopefully looks familiar a little bit. And they go through the process twice on page 150. They do it with inverse tangent and then do it again with inverse secant. And then this was right here was inverse sine. And then y'all did a couple of them on the board before y'all left, but it's been a while. This so they can see y'all. And so they can see him. So 2 is 1.1. Did you just estimate it? Right. Okay. How did you put that? Yeah. Okay. So if I give you a point and a slope, can you find the equation of the straight line? Point and slope. That's what they want you to do, is come up with the y equals mx plus b. Which is going to be the equation of this line. And then just back and you say, well, because that line is changing, it shouldn't. So you got, I feel like it's number 10. Okay, in order to find the derivative of 2, find the derivative of inverse tangent and plug 2. Let me do that with one. Good. Okay, which also, this is the slope, I mean, the graph of inverse tangent, right? And so at 2, it's saying that when you say 1/5 is the derivative, you need the slope is 1 over 5. That's the slope of the tangent line. Yeah. I'm gonna take a little. You can do a ruler. You're gonna hit it. Yeah. That's the edge. Alright, that looks like a slope. Okay, and then with follow a line through the point to f of 2. Okay, so to get f of 2, you already found f prime of 2. But f of 2, you plug in 2 here. Okay. And so this is your y now. So you got a point, 2. Okay. And so, did you get this first? Yeah, so this is your slope at 2. And she figured out what the actual function value is at 2 by plugging 2 in here. And just using our calculator. Okay, and also what she did here in this line is since you got a 1/5, that means the slope at 2 is 1/5, so up 1 over 5. Right? So she started at that point there, up 1 over 5, and down 1 over 5, and drew a tangent line. I think I would have right over there.
I'm not as neat as her though.
Okay, so now can you get the equation of that line? You've got a point. Did you know that that point right there is 2, 1.1? And you know the slope is 1/5. So can you figure out what y equals mx plus b is for that line? Now you idea. Y, you will spell you Y. Okay, now what we did, yeah, so you could write Y equals 1/5 X plus that. And that kind of, like if you went and graph that on here or on your calculator, it should look like that line. And then they're asking you, how does the result confirm that the algebraic formula is correct? Because that line ends up being the tangent line at 2.
So it's just the same one.
Because you use the formula they gave you, if you not 1/5, sure enough, that tangent line has that slope.
Mrs. Belcher,
Yes,
on 21,
yes.
what's the algebraic derivative formula to get the f prime of 2?
That's the one in the book on your formula sheet that says 1/1 plus x squared.
Oh, okay.
And if you need to see me work that, let me know and I can put it on the whiteboard again, like
Okay.
the other one. You already turned yours in?
Yeah, I'm fixing one right now.
Lewis, let me know when you get finished with that. Because that way you'll be finished with the formula sheet, I mean, the quiz.
Yeah. And then do you want me to like take pictures of it and just submit it on the classroom?
But if you're coming back tomorrow or Friday, then you can just turn it in when you get back.
Oh, okay.
That'd be fine. And Brian, did you finish the quiz already?
Yes, ma'am. I'm working on the next section.
That's what I thought. Okay, so as soon as Lewis gets through, I'm going to start talking about that one. I'm going to start going over it since we have quite a bit of time.
Mrs. Belcher.
Yes. Did you finish?
No, I just have one more question.
Okay.
When you're supposed to plot the line through 2 and F2, how do you get it to that the is equal to prime of 2? Like how are you supposed to like plot it?
Okay, so let me get to the screen again so I can show you. There. So they have a graph where it kind of looks like that, I think. And so here's 2, right? And then you found hopefully what f of 2 is.
Yeah.
Did you do that yet?
Yes.
1.1 something? Okay, and so in other words, you have a point here, 2 comma 1.1. And since f prime at 2, did you get that as 1/5?
Yes, I did.
Okay, well, that's the derivative, which means it's the slope of the tangent line, right? So 1/5 is like m. And so what they're wanting you to do is come up with y equals mx plus b, which is the equation of that line, the tangent line. And it should give you the line that is tangent right there. And so in other words, you know that this 1/5 is true using that formula that you had, 1 plus what was x squared or something. You know that this is true because it gives you this for the derivative, and that's the same as the slope, because when you plot this line, you got a tangent line. And you can figure out what that line is because you have a y and you have an x from this point here. And you have the m from right here. So you can figure out what b is. So I think they want you to go ahead and get that equation. And when you graph it either on your calculator or on the paper, it should be that tangent line.
Okay.
And that's about it. Okay, everybody finished that and turned in the quiz, right? So open in your books to page 153. Everybody over there? Page 153. And before we actually get into differentiability and continuity, let's refresh ourselves on what continuity means. So go back to, keep your hand there, but go back to page 47. Way back, page 47. Anybody on 47? Come on. Okay. It says continuity. Do you remember the 3 conditions for continuity? You could tell that a function was continuous at a point if it had a function value. That's the first one. F of c exists, which means there's a function value. It's not an open circle, right? Or an asymptote or something. It actually exists. And then number 2, the limit of f of x has to exist. The limit from the left has to equal the limit from the right. There has to be an actual limit. And the limit has to equal the function value. that all ring a bell? Okay, so that is continuity. And we learned that you can have smooth continuity. Like if you look on the previous page 46, only the first graph, oh no, that's a removal discontinuity. Only the last two graphs are continuous. There's the one that has the cusp, see that one? Over there on page 46. And then the continuous one, figures 2.4F and 2.4G. Those two graphs show continuous, right? One smooth and one has a cusp. Now, do you think both of those are differentiable at that point? We already talked about it a little bit. Can you get a derivative at a cusp? No. Do you know why?
The tangent line could be going any.
Yeah, on one side the tangent line is one way, and on the other side it's the other way, so you don't know what the actual slope is at the cusp. Exactly. Okay, so then going back to page 153, it says that if a function f has a value for the derivative at c, then it is said to be differentiable. If you can take the derivative and find the derivative, a real number, then it is differentiable. That makes sense. That's kind of the definition of differentiable. And then, and this is all repeated again on page 154, so go to 154. The differentiability at a point occurs when there is a derivative at the point, okay, and it's a real number. And then you have differentiability over an interval, an entire interval, if you can say it's differentiable at each point on that interval, right? And then you have differentiability for a function, that's the third one, if and only if the whole function is differentiable on every value of x in its domain, okay? And so they give you two graphs there on page 154, and they show a cusp and they show a smooth curve. And they say that the first one is continuous, but it's not differentiable. The second one is differentiable, and therefore, since it's differentiable, you know it must be continuous also, because in order to be differentiable, it has to be continuous, right? And then they go through a proof on page 154 and 155 that I have studied over the years, and I'm still not real comfortable with their proof, because it seems like they pull some stuff out of a hat, and they talk about at the bottom, the secret to this proof is to multiply by 1 in the form of x minus c over x minus c. And I don't know, the whole thing is kind of shady to me if you ask. But it's supposed to be a proof of the fact that if f is differentiable, then f must be continuous. Okay, and it kind of makes sense. If a function is differentiable, which means smooth, then it's also going to be continuous. Because if it wasn't continuous, you'd have a gap. That's not smooth. Or you might have a cusp, and that's not smooth, right? And so the main idea for this section is on page 155. Differentiability implies continuity. Differentiability implies continuity. And I always challenge my students each year to see if over the next week or so you can come up in normal conversation with people and use that sentence. Differentiability implies continuity. What do you think? Like you could say, what, am I hungry? What, does differentiability imply continuity? You just close right out. And so another thing I wanted to show you, I guess I can do this on the board, but I would have to turn them off, is because they talk about contrapositive in that box there. Okay, and so do you remember using Venn diagrams? The probability and that kind of thing. Okay, and so all of this, this big circle means continuity, represents continuity. All the functions that are continuous. And then in this the smaller circle are all the functions that are differentiable, say at a specific point, okay? And so if you have a function that's differentiable, it's in this little circle here. And so it would have to be continuous, right? because every differentiable function is in the set of continuous. It's kind of like having a circle where this is the big circle refers to all dogs, and this little circle might refer to chihuahuas, which I don't know how to spell, but I think it's like that, right? So if something is a chihuahua, then it has to be a dog, because chihuahua is a subgroup of dogs. And so if a function is differentiable at a point, then it must be continuous at that point. Okay, now they ask about the inverse and the converse, and I get those mixed up sometimes. Let's look at it this way. P implies Q. And so what we're doing with P and Q is we're saying differentiability implies continuity. Well, let's see if I can stop. Okay, differentiability implies continuity. Would you say that continuity implies differentiability? And would that be true? If something's differentiable, if something's continuous, it has to be differentiable? No, because you have a cusp, right? It'd be continuous but not differentiable. So that doesn't work. And I'm not sure if that's the converse or the inverse. I know one of them is, I think it's the, y'all remember, guys? That if you have P implies Q and then you say Q implies P, that's inverse or converse. So the other one is if not P, then not Q. So could we say if not differentiable, then that always implies not continuous? Would that be true? All right, can you think of an occasion where it's not differentiable, but it is continuous? A cusp, when you have a cusp, right? And so that's not true either. So the converse and the inverse, whichever ones that are, those are not true. But the contrapositive, you remember what the contrapositive is? Not Q, they put a little prime thing there for not, or a little tilde. I think I've seen different ways. Let me write it with just the words. Not Q implies not P. So that would be in our case, differentiability implies continuity. If not continuous, then not differentiable. Would that always be true? If it's not continuous, it's not differentiable. That would be true. Okay, and so differentiability implies continuity is always true. And if it's not continuous and it's not differentiable, that's always true. This statement, differentiability implies continuity, it and its contrapositive are always true, but the inverse and converse are not necessarily. So why are we even learning that? They mention below on page 155, below the gray box, this property and its contrapositive provide a simple way to prove that a function is continuous or not differentiable, respectively. So look at example 1. I like these kind of problems because as soon as you realize what it's asking, it's so easy. But figuring out that it's asking is difficult. It says prove that f is differentiable at x equals c. No, not that. Not where I am on 155. Prove that f of x, page 155, equals x squared minus 7x plus 13. Is continuous. We're kind of proving this. Prove that this is continuous at x equals 4. Yeah. Okay, so how can we prove that this is continuous at x equals 4? Well, what we can do is we can take the derivative, find f prime, which is 2x minus 7, right? Is that right? And then find the derivative at 4, which is 8 minus 7 is 1, right? And so we found the derivative at 4. And what's our statement? Differentiability implies continuity. If it's differentiable at 4, which it is, because we got a 1 here, then it must be continuous. So we just proved that. All we had to do is take the derivative. Okay, that's pretty fun. And then look at example 2 on page 156. is the function g of x, and they have a rational function there, differentiable at x equals 2. Is it differentiable at x equals 2? Well, what would happen at x equals 2 for that function? Because look at the denominator. If you plugged in 2 for x, what would you get in the denominator? 0, right? Can you divide by 0? No. And so in other words, it's not continuous there. So you could say, what about its differentiability? That it is or isn't? It's not. That's the contrapositive. You could say, it's not continuous at 2, so it can't be differentiable there either. That make sense? So you just proved that. And then it says the most significant thing for you to understand here is the distinction between the concepts of differentiability and continuity. To help you acquire this understanding, it helps to look at graphs of functions and state which, if either, of the two properties apply. So look at example 3. So on example 3, you have A, B, C, and D graphs, and you're supposed to state if they're differentiable or continuous at C. So on A, is it differentiable at C? No, right? It's not. Is it continuous at C? Yes, but it's not differentiable because we're going to assume that's a cusp.
Wait, so can you like define that again? Like, does that mean it doesn't connect or?
It does, it's continuous, and so it connects. If you were to draw that graph, you would never have to pick your pencil up off the paper. So it's continuous, but because you have to stop and change direction all of a sudden,
So it's like a change in direction.
yes, that's what a cusp is, a sudden change in direction. And that means that you just changed your slope. And so what, you got a slope over here of this, and you got a slope over here of that, but what's the slope right there at the tip? You can't get the slope. That's right at the tip. And so that means that it's not differentiable. And so if it's not smooth, it's not differentiable, even if it is continuous. And then on B, is that continuous? No, right? At C, it's not continuous. So is it differentiable there? No. What about C? Is it differentiable? Is it differentiable on C? ABC at point C? You see the removable discontinuity?
Oh, okay. So
If there's,
it can be, so if it's not continuous,
even if it's,
it's not.
yeah, you don't even consider that smooth. There's a hole there. You have to all of a
that
sudden
would have
jump.
been, okay. I
You're
see.
not continuous. It's not smooth.
Okay.
It's kind of like when you're walking on a sidewalk. There could be like a gap between this block and that block, and you step over. Or maybe it's just the ground is shifted, so it's like that. So anything like that is not smooth, and it's not differentiable in. But if it's a cusp where they're still connected, it's still continuous. But it's when they're not connected, it's not continuous. Okay, and then at D, that was tricky because you're looking at point C. When X is C, it's differentiable and continuous, right? No matter what's happening over there on the first quadrant, doesn't matter. Okay. Now then, look at example 4. We've done some of these, something like this, and I'm going to put this on the whiteboard, the virtual whiteboard. Make sure the guys can see it good. Any questions so far? No. What I'm going to do in example 4 is very similar to some problems you'll see on some quizzes and homework problems and the final probably. Okay. Move that up and that out. Okay, so we end up with we start with a piecewise function, piecewise defined function. So the function is equal to ax cubed if x is less than or equal to 2. Let me move this so y'all can see better. I'm not in the way. But it's equal to b times x minus 3 squared plus 10 if x is greater than 2. Okay, that makes sense? And this 10 looks kind of funny. So this first one is a cubic function. You can kind of picture that, right? The second one is a quadratic. And we've got some variables here that we're going to figure out what A and B have to be. Okay. And so it says, use one-sided limits to find the values of the constants A and B that make piecewise function f differentiable at x equals 2. And it can't be differentiable unless it's what? Continuous, right? And in order for it to be continuous at 2, continuous at x equals 2, you would have to, the y value for this first branch would have to equal the y value for the other branch. Remember doing these before? And then you plug in the 2 for the x. So you'd have a times 2 cubed equals b x, oops, undo, 2 minus 3 squared, okay? The only problem is we can only simplify so far. Like this is going to give us 8a, and that's 2 minus 3 is negative 1 times squared is going to be positive 1, so we'll just have a b here. So we can get it down to this far. So we still don't know what a and b are. We just know that b is 8 times bigger than a, okay? But if we want to know if it's, we got to know that it's continuous too, which means there can't be a cusp, which means that the slope of this branch has to equal the slope of the other branch. Okay, and the slope is the derivative. So differentiable, you want to see what happens if it's differentiable at x equals 2. Oh man, it's hard to draw. Okay, that means you have to set the derivatives equal to each other. Okay, the derivative of the first branch is 3ax squared, right? If I take the derivative of ax cubed, I get 3ax squared. And I'm going to set that equal to the derivative of the second branch, which I'm going to bring the 2 down in front. So I'll get 2b x minus 3 to the 1 power. Oh, I don't need a 1 there. And then plus 10, the derivative of 10 is 0. So I just have this right here. And then I'm going to plug 2 in for x. So that'll give me 3a times 2 squared equals 2b.
Why did you put the 3 in there? Like what let you do that?
Do what?
What let you put the 3 in there?
The 3 into for x.
No, you put like a 3 in front of the ax.
Because I was taking the derivative of this. So I bring the 3
okay.
down in front and then make it a 2.
And then are you taking the derivative of b to match that?
Yeah, so I bring the 2 down in front. So I got 2b. And then I just have a, instead of a square, it's just a 1 here. But this is taking the derivative of both sides because they have to be, the derivatives have to be equal to each other, or so that the slopes are equal to each other at this point for it to be smooth. No kink. Okay, and so in this case, okay, let's see if I can move that away there. That's 4, so that's going to give me 12a equals, and that's going to be negative 1, negative 2b. So again, I'm stuck with an a and a b, but, and even here I can divide both sides by negative 2 and give me negative 6a equals b, right? I did that right. But I have 2 equations with 2 unknowns. So what can I do with that? Since both of these are equal to b, I can just set 8a equal to negative 6a. And am I doing this right? That looks kind of funky here. Plugged into 4, 12. Plugged into, get negative 1, negative 2. And I plugged in B for A. Because when you divide both sides by A, we're getting a, okay, what did I do? Let me look in the book. Yeah, B equals negative 6A. So like, we got this part right. Oh, okay, so somehow the 10 is in here. Ah, I see what I did. Okay, when I put these equal to each other, I didn't have my plus 10 over here. Darn. Okay, so I'm gonna have to change this up a little bit. Let me get my eraser. The bottom part's all correct. I just gotta fix the top. Okay, so this gives me A equals, that's -1, so that's B plus 10. And so I can just subtract 10 from both sides. So B would be equal to A minus 10. Okay, and so let me erase. Let me keep that. I want to erase this, yeah. Okay, and so let's use this equation with this equation. So we can set -6A equal to 8A minus 10. So I'm going to subtract 8A from both sides. -14A equals -10. So A equals 10 over 14, which is 5 over 7, which I think is what we got. And then we can figure out what B is. I'll go over here. So we said B was equal to -6A, right? So B is -6 times 5 over 7, which gives us -30 over 7. And so if we went back to this original function up here and we plugged in for A, we plugged in, what did we say A was? 5/7. And then for B, we plugged in -37. Then we could be assured that those two branches are going to meet smoothly with each other. Does that make sense?
What is A down there?
5 over 7. So I just divided both sides by -14, the negative canceled, then I divided by 2. Yeah, it's blurry. I can't get it where it's focused up here and focused down here.
And then you can, how do you get the B that you got?
Then I went over to, since I knew what A was, I knew that B is equal to -6A. So I wrote that here and plugged it in.
So if in the end they equal each other, that's, or like how?
So you're just trying to find out what A or B is because you have two branches of a function. And sometimes you've seen those where they, maybe it'll be like, this is an example of a piecewise. Maybe you'll have a line coming over here and then you'll jump up here and then have a parabola going or something, you know, and that's a piecewise function. This is one branch, that's the other branch. We want to make it so that the branches meet and are smooth right there. Okay, and so the first thing you do is you set the two branches equal to each other. That's what I did here. Plug in your point where they meet, and then get your equation as simplified as you can, and then take the derivative of both branches and do the same thing, and you'll get another equation. And then by having two equations, you can figure out what both A and B have to be. Don't have a lot of time, and so that's pretty much, they show this over on page 157, and look at the graph on page 157. You can look here. They actually show how if you did graph that exact thing, you'd have a nice smooth graph there at 2. Okay, so we're going to work on the problem set tomorrow in class. And some of you have already got started on the cues and everything, maybe. So that's all we're going to do today. Any questions? Let me see if I can get the
This
guys.
was to get what? Like what were they asking for you to start that process?
They were asking that you got these two branches, and I want to know what constants do I need to stick in there so that the two branches will be continuous.
How did they word it?
They say use one-sided limits. That's probably confusing. by one-sided limits. I mean, like normally, if you want to find out what the limit is in a function, you just plug a value in and solve. And so that's what you're doing. By doing the process I just went through, I was using one-sided limits. Use one-sided limits to find the values of constants A and B that make the piecewise function differentiable at x equals 2. The piecewise function differentiable. Yeah. And if you get on a test or a quiz where you're not understanding what the directions are, just let me know and I can explain it. Yeah.
Can you check my cues?
Yes. Okay. So what'd you get for Q1?
Let me go for you.
Use the 3 cases there. 7 on the FSD. Yeah, that works. So this is 9.
I gave the
You would
graph-
say slope of a tangent line is after the meaning of derivative, the meaning.
They asked for the definition, and I was like, there's 2, so I just picked the short one.
Normally the definition is the equation with the h minus f of x minus h minus f of x. You know that
Yeah.
the limit as h approaches 0 of all that. And when they were looking for slope, they usually say what is it?
It seems like whenever they ask for the definition, it's so nuanced.
Yeah, it is. And so I'd be pretty lenient on something like that, but I bet
You
that's
take
what-
that?
Yeah. And then you took the derivative from this. Oh, finding y, gotta go backwards. Yeah, okay, that's right. First one is -9. Measure just needs that. If you said you took the derivative twice and you plugged it into on Q9, what did you do to get the integral from -2 to 2? Did you count squares?
Yes.
Okay. For the function.
That one, I was confused with. So I was like,
No, it's a negative slope. So when they take derivative, we're going to slope. And since it's negative, it's not going to be greater than 2.
so it'd be
So they're looking
minus
for
1
the
e
slope.
less than -1, because it's
Yeah.
-2.
Yeah, I would say E.
That one was the one I was confused on, and I saw, the slope was like, oh, I see 2, it's going to blocks. I guess I just didn't.
Yeah, for the negative right. All right, well, I'm going to hang up on you guys so I can get together with my chemistry kids. Any last minute questions? All right, see y'all later.